Solve y prime prime plus 3y prime plus 2y equals to 0. So following what we just did, I write down the characteristic equation. Lambda squared plus 3 lambda plus 2 equals to 0. How do we solve quadratic equations? Factoring, right? Or completing the square. That's the best way. Plus 2 lambda plus 1. And so what do we got? We got lambda 1 is equal to minus 2, lambda 2 is equal to minus 1. These are my solutions to the characteristic equation. And from that, what do I get? I get two things, right? I get y1 equals to e to the minus 2x, and I get y2 is equal to e to the minus x. These are both, they both solve y prime prime plus 3y prime plus 2y equals to 0, right? Is this course easier or harder with me covering or not covering this section? I submit to you this course is easier with this topic, right? If you have a test, you have 3 questions, right? You have 3 questions on section 9.1 and 9.2, or you have 2 questions on 9.1 and 9.2, and you got 1 question on this. In other words, you got 1 question where all you got to do is solve a quadratic equation to write down solutions. That is whack. I don't know. It's astounding to me it's that simple. Now, what's the general solution, right? Let me show you an example. Example or theorem, you choose. What do you guys want? Example or theorem? Choose your own adventure. What do you want? What's that? Example. All right. I'm going to come back to the theorem eventually anyway, so don't worry, the rest of you. So here's a different one. How about this? Y prime prime equal to 0. Can we solve this second order differential equation? Integrate once. We get y prime is equal to c2. Integrate another time. We get y is equal to c1 plus c2x. If there's any justice, right? Since this is essentially, I mean, wouldn't it be nice if what happened here has to happen for all possible differential equations of this form, in the sense that, like, there's going to be 2 integration constants, right? So if I trust our intuition, it suggests to us that up here, the general solution is what? Y equals to like c1 e to the minus 2x plus c2 e to the minus x. I'm arguing by intuition, very dangerous. But you can check, in fact, that a linear combination, a so-called linear combination, if only I had some class where I gave a technical explanation for what that means. Oh, well, no one here would possibly be taking that class at the same time. Let's see here, you know who you are. So this is a linear combination of e to the minus 2x and e to the minus x, you know? And in fact, that is also a solution to y prime prime plus 3y prime plus 2y equal to 0. In fact, what I've just written, this is the so-called general solution. This is the general solution. The star. This being star. Okay, I'm tired of writing it. The general solution has what? It has all possible responses to different initial conditions. For a second order differential equation, it's not enough to specify just one initial piece of data. You need 2. Like if you want to think about it, physics, this would be like the second derivative is like acceleration, right? So if you've got the acceleration equal to something, in order to find the position as a function of time, you need to know both initial position and initial velocity, right? This is the mathematical cousin of that. All right. Oh, there is something. Yes, sir. I mean, I haven't proved that. Here, let me make that intuition a little bit more formal. Theorem. If y1 and y2 solve ay prime prime plus by prime plus cy is equal to 0. In other words, I'm claiming this without proof, just by analogy. Ay prime prime plus by prime plus cy equal to 0, then c1y1 plus c2y2 solves star. In other words, if you have two solutions, if you take any linear combination of those solutions, you again have a solution. How do you prove this? Not that hard, really. So let's look at the proof here. So we have what? We're given y1 and y2 solve star, right? So I can look at a times c1 y1 plus c2 y2 prime prime plus b times c1 y1 plus c2 y2 prime plus c times c1 y1 plus c2 y2, right? I can look at that expression, and I can simplify it using properties of calculus. Second derivatives, how do they work? Can you pull constants out of a second derivative? Yes, search your heart. You'll find it's true. Does the second derivative satisfy the sum rule? Second derivative of sum is the sum of the second derivatives. This is also true. So I can rewrite this as like a times c1 y1 prime prime plus c2 y2 prime prime plus b times parentheses c1 y1 prime plus c2 y2 prime. Pull the constants out of the derivatives, and then finally over here I've got c times c1 y1 plus c2, and nothing to do over here, c2 y2. And then I just group stuff. I've got like c1 times a y1 prime prime plus by1 prime plus cy1 plus c2 times parentheses a y2 prime prime plus by2 prime plus cy2. There's a lot of writing going on here, but not too much thinking. Not too much thinking. Mostly just that the second derivative of the sum is the sum of the second derivatives, and you can pull a constant out of the second derivatives. And then what do I have then? What was I was given what? What does that mean about the terms in parentheses? Right, this is 0, and that's 0. So the whole thing is 0. So therefore, y equals to c1 y1 plus c2 y2 solves star. There you go. We've settled it once and for all. If you find two solutions to a second order constant coefficient ODE, their linear combination is once more a solution. There is something I'm assuming here that's important, and that's that this is what's called a homogeneous. This is a homogeneous ODE. That's a somewhat unnecessary comment in here because we only study homogeneous ones for the second order case, all right? You should be warned, though, that this is no longer true in the non-homogeneous case. In the non-homogeneous case, the sum of solutions is no longer a solution. It's a little bit trickier. But, you're going to take a course in differential equations, many of you, and I leave that for that course. Of course, I'm happy to talk to you about how that works out in office hours if you're curious. If you just can't wait to find out, I can tell you. It's not that complicated. When I taught Calculus 2 at NC State a few years ago, we covered the non-homogeneous case in Calculus 2 as well. But I think Calculus 1 at NC State now includes trig substitution, partial fractions, integration by parts, and the whole thing. So their Calculus 2 has a little bit more wiggle room. All right, any questions about this? So you see I've replaced intuition with theorem. Okay. Yes, sir. Oh, that was just stretching.
What is this application?
Oh, what are applications of this? Okay, sure. For example, if you have like a spring attached to a mass, all right? It's all inside like Jello, something like that. Then the mass times the acceleration, all right, will be equal to the spring force, which is minus kx. And then a reasonable approximation to the damping due to Jello, something like minus beta v. All right, where v is equal to dx dt. So what this really gives us is m x prime prime plus beta x prime plus kx equals to 0. Right, and there you go. That's a second order constant coefficient, ODE, that describes motion of a spring, of a mass under spring force with damping. Another example would be this, and one of these guys, like that. So this is a capacitor, this is a resistor, this is an inductor, and if I remember right, you can talk about the sum of the voltages, and so like the sum of the voltages have to be 0. So 0 has to be equal to like I times R. That gives you the voltage on the resistor by Ohm's law. Man, the voltage on the capacitor, C is equal to Q over V, I think. So V is Q over C, right? And then the inductor, goodness gracious, I think it's L di dt. I'm a little rusty. Okay, but the thing about it is I is actually equal to dq dt. So that's actually, so that means that in fact the di dt is actually q prime prime, right? So after the dust settles here, what you got is you got L q prime prime plus R q prime plus q over c is equal to 0. So that's in fact the same mathematics. There's a dictionary between here. Mass is like inductance, resistance is like coefficient of damping, and the spring constant is like 1 over the capacitance. So everything mathematically you learn about springs, you've also learned about RLC circuits. I don't know. There's more, of course. These are central applications, but now, what's the motion of a spring? If you just take a spring and you give it a pull and let it go and it has no friction, essentially, what does it do? Yeah, I see somebody's clapping. But the thing, yeah, that's true. But we fixed one end of the spring, so what it does is like it just goes like this, right? Although I suppose that's also clapping. I guess that's a question. Do you clap like this? I mean, like that. That's more refined. Very good. My clapping is very boorish. Perhaps I'm a Trump supporter. Let's see here. I'm sorry. Oh, no, now I have to edit the video. Well. All right. My point to you is that's sines and cosines, right? The exponentials don't do this with time. Right? So I've started us with e to the lambda x as a solution, right? But look at what just happened in this example. X. Is x an exponential? No, it is not. So apparently there's more than just exponentials in the solution, in the world of solutions, right? The answer, I'll just tell you the answer. I'm not sure if I have time to properly derive it yet. I think I've given you indication for why there has to be, oh man, well, it's just going to have to wait for tomorrow. Sorry.